You know, we usually think of math as this world of perfect, predictable rules. But what happens when those rules don't act like they're supposed to? What if an error that keeps popping up isn't an error at all, but a signpost to something much deeper? Well, that's exactly the journey we're on today, as we explore the geometry of hidden structures.
In this quote right here, it gets straight to the point. It talks about a canonical twist that looks like an accidental defect. You know, something you'd want to fix. But it turns out it's the main event. It's not a bug, it's the signature of how things really work. It's a clue. Now, we're pulling all these ideas directly from the paper Conformal Twists and Geometric Pseudofunctoriality, which was written by Mohamed Ben Ammar Chraiti. You can see his email and the work's DOI right there. This paper takes what looked like a frustrating problem and turns it on its head, revealing it as the cornerstone of a whole new theory. Okay, so let's set the scene. A theory's unexpected twist. Imagine you're a mathematician, and you're trying to build the perfect ruler, a tool that can measure the properties of really complex geometric spaces. The number one rule? It has to give you the same consistent result no matter what. So, this mathematical ruler has a technical name, a fundamental Spinorialian complex. But really, you can just think of it as a super sophisticated tool designed to create a consistent measurement, like a unique fingerprint for any geometric landscape you pointed at. And the whole idea is to use this fingerprint to compare different spaces. And this slide lays out the conflict perfectly. On the left, you've got the dream, a nice, clean, predictable measurement. But on the right, you see the reality. When mathematicians tried to carry this ruler from one space to another, the measurement itself got all twisted and distorted. The tool just broke. All that consistency they were hoping for was gone.
It's the obvious question, right? Did they build the tool wrong? Was there some kind of flaw in the design? What happened? And this is where the story takes a brilliant turn. Instead of trying to fix the bug, the author reinterprets the whole thing as a feature. They decided not to get rid of the twist, but to lean into it. Because it turns out, the twist isn't the problem, it's the beginning of the solution. Here's the core insight. That twist isn't just random noise. It's a signal. It's the math telling us that our map of this world is way too simple. The reality is much richer, and we're going to need a whole new framework to actually understand it. I love this quote from the paper's abstract. It basically says the failure of the simple approach isn't a defect in how the tool was built. It's an intrinsic feature. In other words, the math is doing exactly what it's supposed to do. It was our expectations that were wrong. So the very first step was to get a handle on this twist. It's kind of like trying to measure a single specific thread in a giant tangled mess. By isolating something called the conformal correction term, the twist went from being this weird, mysterious distortion to something you could actually predict and manage. All right, so when you realize you're exploring a whole new kind of landscape, you need a better toolkit. You can't navigate a 3D world with a 2D map, right? So to build these new maps, they had to invent entirely new mathematical tools from the ground up. The first new tool is something called a bi-category. Okay, think of it this way. A normal map has points and it has paths that connect them. A bi-category is a richer map. It has points and paths, but it also has paths between the paths. It shows you how you can morph one route into another. And that extra layer of information is exactly what was needed to make sense of the twists. And of course, if you've got a brand new type of map, your old compass isn't going to work. You need a new one. And that's the pseudofunctor. It's a much more flexible navigator that's built to work on this new bi-category map. It understands the twists from the get-go, so it accounts for them, and everything finally lines up perfectly. So what the paper pulls off here is building this really elegant bridge. It uses the pseudofunctor to connect the original, kind of messy world of measurements with this new, highly structured, and much more sophisticated bi-category. It provides the missing organizational framework for the whole thing. But what about the twists themselves? Are they just a bunch of random corrections, or is there a pattern hiding in there? This is where we get to the most profound part of this whole discovery, actually decoding the twist. The process was just methodical and beautiful. First, just observe and measure every single twist. Then, organize all of them into one big family. And when you look at them all together, something amazing happens. A pattern emerges. They're not random at all. They form this coherent, predictable structure. a beautiful mathematical object called a normalized two-cocycle.
And that's the mic drop moment. The scattered errors, the twists, all the stuff that looked like a mess. It wasn't chaos. When you gather it all up, it forms its own elegant, perfect mathematical object. The solution wasn't just a fix. It was the discovery of a whole new structure that was hiding in plain sight the entire time. So, what does this all mean? Well, the paper's conclusion is that this work gives us a whole new language for this area of geometry. It's a language that actually embraces how complex the system is, instead of trying to simplify it away.
All right, let's boil it down to the key takeaways. First, the twist isn't a flaw, it's an essential part of the story. Second, the system naturally works backwards, a property that mathematicians call contravariance. Third, that hidden pattern we found, the two-cocycle, is the very thing that governs the rules of the system. And finally, the theory's true identity isn't simple. It is, by its very nature, twisted and higher categorical. That's just what it is.
And this whole thing leaves us with a pretty big thought. This story, from the world of pure math, feels kind of universal, doesn't it? It just makes you wonder, how many other errors or anomalies out there in science aren't mistakes at all, but are actually clues, pointing us to a deeper, more beautiful reality that we just haven't learned how to see yet.